Hello viewers, my name is Jeff, a math teacher, ready to teach you a topic, further logarithms. It's a Form 3 topic. Welcome. So, further logarithms is a kind of continuation of a Form 2 topic, indices and logarithms. So if you are in Form 2, at least you are aware of it. So this is a continuation, but kind of slightly in a different way. So there was indices, then there was logarithm, and the applications, if you remember that. So by the end of this topic, you're supposed to be to have learned or be aware of things like how to change logarithms how to change indices to logarithms to indices, that is logarithmic notation. You should be also be aware of laws of logarithms, which are used to simplify expressions and also solve equations. And then further, the other thing that you need to know about the topic later on is further computation using maybe logarithms. That will come later on. So to start with, just in that order, I'll begin by, first of all, explaining a logarithmic notation. Indices. In Form 2, you have indices. If I write a number like a raised to m equals to n. This example, we say this is in indices form. And what makes it indices is this. Any number which is raised to is referred to as an index. And if there are several of them, then we call them indices. That's plural. So this is indices. So the first thing you're supposed to know about the topic is learn how to change indices into logs. If you want to change this statement into logs, then you write log. The answer, which is n, becomes the log. Then this a becomes the base. Then the power becomes the answer. That is it. So it is log n base a equals to m. Now on real values, something like 2 raised to 3, of course the answer is supposed to be 8. But now, if you want to change this into logs, it has to be log 8 base 2 equals to 3. So you have to know this because it has its own application. Maybe now and mostly later on in the topic, especially if we are doing equations. So, but for expressions, maybe not really that much, but at least you must have the concept. So it's not only changing indices to logs. You have to know how to change indices to logs and also logs to indices. For example, if I have a statement, log x base y equals to, say, c. Then from this, if you want to change logs to indices, has to be y raised to c equals to x. So I hope you notice that. You have to know how to deal with these values in this case. Something like log 125 base 5 equals to 3. Then it's supposed to be the same as 5 raised to 3 equals to 125. Okay, at these early stages, the application may not be that much, but just with this slight little explanation that is there, you can actually get a question that you need this concept to solve. For example, if you're told to solve this, there may be a question which says, given that log y base 5 equals to 2 and log x base 2 equals to 3, find the value of xy. Listen to the question carefully. The question is, given that log y base 5 equals to 2, log x base 2 equals to 3, solve xy. So if you want to solve this, then if you have the concept of changing logs to indices to logs, then you can use that concept to actually solve this. So what I need to do for each of these values is change this from logarithmic notation to index notation, which will be, this will be the same as 5 raised to 2 equals to y. And this statement here would be the same as 2 raised to 3 equals to x. And then of course the value of y equals to 25 and the value of x here equals to 8. So then the question was solve xy. So the value of xy in this case should be 25 times 8, which is equals to 200. So I think you can see that I've used the concept of just simply changing indices to logs and vice versa to solve such a question. If I didn't have the concept or knowing how to do that, then such a question, there's no way you can actually solve it. So I hope you notice that. Okay, that said, now that you're aware of how to change logs to indices and vice versa, the next thing, which is now the main thing in the topic, is learn how to now solve or work out operations to do with logs. But this is a topic that has rules, and that's why there is laws of logs. Laws of logs are the laws which are used to do any operations to do with the questions which may be expressions or equations in terms of this topic. So there are several laws. Today we focus mostly on three of them. It is very hard to use only one law to give you like all the application as it's supposed to be. But I'll try and make sure that anytime I explain any law, I'll try to show you how you can use the law in solving out maybe questions relating to it. Now, what will happen is, once you are done with all the laws, then it's very easy to come up with a question that actually might use the concepts in the laws to solve the questions. So there are several laws, like I've said, the major ones being 3, I'm going to explain. And any application I use today will only be questions relating to logarithmic expressions, not equations. Then later on, we can use the same laws in equations, but once you are familiar with how to use them in expressions, the other part will be easier to explain. So now, that said, the first law will be log A base x plus log B base x equals to log into brackets AB then base x. Okay, some few explanations before I actually talk much about the law. First of all, notice that logarithms form 3 is about logs to any base. That's the first thing. Logarithms form 2, which was an introduction, was only about logs to the base of 10. And because of that, you didn't really need to write the base. If you write a statement like log 8 without a base, it means the base is 10. So form 2 was basically logs to the base of 10. Form 3 is logs to any base. And that's why I'm including a base here. Which means when you talk about these laws of logs, there's some things you have to notice. This law will only be possible if the bases are the same. So it says, if you have two logs which are being added, but they have the same basis, that's possible. Then the answer you get is, if there's an addition sign, multiply the respective logs. This is A and B, and that's why I have A, B, the same base. In case this base was different, then this law will not apply. It only applies for questions where the bases are the same. You have to note that. So now, in a basic example of a question to explain this, something like, if you're told simplify, we say today we're only looking at examples to do with expressions. Then maybe later on there will be questions. I will still explain. Simplify log 6 base 3 plus log 4 base 3. This is possible. Why? Because the bases are the same. So since the bases are the same, we can actually add this. And according to this law, then the answer should be multiply the respective logs, which is 6 times 4. 6 times 4 is supposed to be 24. then remember to show your base. If you don't indicate the base, then it means you've changed the base to 10, which would be wrong. So if the base is not 10, you have to make sure that you have to indicate the base all the time. So this is a basic example. Then, but I never said that this is a question you expect in an exam. It's just something that leads you to the main concept that you actually require. So then, once you have this concept here of having individual logs added to get an answer, the next thing you have to know from this is how can you, if you have this one block logs answer, can you use it to get the other values? Then I have something like log, say 6. Can I split this in terms of 2 logs? It is a very necessary thing in this part of the topic because maybe most of the applications that come in require that concept. So you might be asked, write log 6 in terms of log 2 and 3. So 6 is the same as 2 times 3. Then this means log 6 is actually the same as log into brackets 2 times 3. And according to this law, if there is times, then it means to split. Where there is multiplication sign, you add the values. So the final answer for this is supposed to be log 2 plus log 3. I notice one thing. I never indicated the bases. So what does it mean? Basically, the bases in this case are 10. So if the base is not shown, we can assume that the base is 10. But if you show, then it's a different base. So now, using this concept here, the application of the first law comes in such questions. And now this is an important thing that you need to understand. And this is kind of like a question you actually expect in an exam now. So they'll ask you this. Given that log 2 equals to 0.3010 and log 3 equals to 0.4771, without using a table or calculator, solve or find the value of then several numbers there. Let's start with the first one, which is log 6. So what this means is I have log 2, I have log 3, but I'm given a different log that I'm supposed to solve. So the only way I can solve this is try write 6 in terms of the values that are given. And one thing, I didn't mean that all the time they'll talk of log 2 and log 3. There can be any different logs, but whichever values that will be given and what is asked simply means you can write this value in terms of what is given. So I repeat my question, given that log 2 equals to this, log 3 equals to this, find log 6. Then this is what I'll do. I'll write this log 6 in terms of 2 and 3, which is the same as log into brackets 2 times 3. Which is the same as log 2 plus log 3, according to this law there. Then they said log 2 is this, and log 3 is this. So what you do is, just substitute those values. Any place you see log 2, you put this value. Any place you see log 3, you'll put this value here. So this becomes, log 2 is 0.3010, plus the next one is 0.4771. Which is equals to, now adding that, it's 0.3010, 0.4771, 18770. I hope my addition is okay. Then the final answer should be 0.7781. That's supposed to be the value of log 6. Now, they said without using tables or a calculator. How that is clearly shown here, it's in the explanation. I've shown all my steps clearly. And I don't think there is a problem using my calculator now just to add these values, provided I've indicated them to get the final answer. That's still okay, because when they say without using tables or calculator, they need to see all the calculations there clearly. And I've shown all the method, everything clearly until I got the final answer. Next, still using the same values. It could have been find the value of log 12, log 12. How do I get 12? Log 12 will be given as log 12 in terms of 2 and 3 should be 2 times 2 times 3, which is equals to log 2 plus log 2 plus log 3. Now, this part here, if I introduced another law, maybe there can be an easier way of actually solving this, but since I only explained this, I'll stick straight away to what I explained and showing everything as far as what I've talked of so far. But maybe later on in the topic, we might change on how we look at this here. So the answer for this would be replace these values. Like I explained before, so it should be 0.3010 plus 0.3010 plus 0.4771. So then, just like I did the other question, add these three values to get the final answer there. Another example, still on the same. There can be a question like this, slightly different, and I really want you to get the concept in it. They said given that log 2 is this, log 3 is this, find the value of, then it's now log 60. Now this 60, I don't think if there is any one way I can write 60 in terms of 2 and 3 alone. It's kind of close to impossible. But now, 60, when you see such values where you need something else rather than this, maybe the only numbers that you can use in this case are what you call the common logs. Common logs are like log 10. Later on, maybe we might explain, but log 10 is 1. Log 100 is the same as 2. Log 1,000 is 3. Log 10,000, 4, maybe, and so on. So there's a time I'd explain why 1, 2, and 3, but for now, just know that these are common logs. You don't need a calculator to get their values. So because of that, and the question was clear, it said that without using a calculator or tables, I don't need a calculator or tables to do this. So because of that, I can include that value in this statement. So now 60 would be the same as log into brackets 2 times 3 times 10, which is now possible. I never used any calculator. I have these values. Log 10 would be a common log. So this is the same as log 2 plus log 3 plus log 10. Log 2 was 0.3010. Log 3 was 0.4771. Then log 10 is actually 1. So if you add these three values together, it gives you the final answer, which is 1.7781. That is it. So now what I've introduced here is something to do with a common log, which was not asked in what you're given. So take note of this. It's a very special thing. It can really help you in this. Without knowing what it is, then you can't actually solve such questions, which will not only involve the numbers that are given. So this means if I had something like 1,200, I could have used 2 times 2 times 3 times 100, maybe. Is it 100 or 1,000? Okay, the second law. So basically, the few things I can explain about this law in relation to expressions, it's what I've done. And this is a kind of question that you should watch. You do any law, there is a reason for that. You don't just mention laws, then you can't even apply them in any question. So if there is this, then there is this. This is a direct application of that kind of law. The second law. The second law, like I said before, we are going to explain at least 3 laws today. So the second law is log A base x minus log B base x equals to, the answer should be, in this case, A over B, then the same base. I've already done most of the explanation. These laws will only apply if the bases are the same. That's one thing you have to notice. That's why it's always XX. If the bases were different, this will not work. Only works if the bases are the same. So now, you might have noticed some difference. In the first law, it was addition. In the second law, is subtraction. Now, when there was addition, we multiplied the respective logs. Now, if it's subtraction, we divide the logs. So that's why log A base x, log B base x equals to A divided by B. In a simple question to explain this, if I had log, say 15 base 5 minus log 3 base, let me use base 4, then base 4, the answer for this should be log, then 15 divided by 3, 15 divided by 3, then base 4, which is actually the same as log 5 base 4. So that should be that clear. Okay, this said, let's now look at the main application of this law. Like I just explained the first case, you always look at the main applications and how questions should be asked in an exam. So using this law, and the same example of maybe question I used in the first law, if you're told, given that log 2, of course it's base 10, equals to 0.3010, and log 3 equals to 0.4771. What kind of questions will relate to this law? So they'll ask you something like, use this law, not really use this law, but without using a calculator or tables, find the value of a first question, say log 1.5. Okay, 1.5. Think of 1.5 in relation to 3 and 2. How can you do an operation to do with 2 and 3 to give you an answer which is 1.5? It's obviously if you say 3 divided by 2. So then 1.5 is the same as log 3 over 2. But this statement here is the same as log 3 minus log 2 according to this law. Then which means once I get these values and I was given the respective values, now it's simply simplify. Now when you're simplifying this is substitute the values. Log 3 is the same as 0.4771. So I'll come where there is log 3, 0.4771. Then log 2 is the same as this. I'll write 0.3010. Then again subtract this value. And if I subtract this, it's 0.4771, 0.3010 minus, the final answer should be 671, then 0. So it means the value of log 1.5 is supposed to be 0.1761. That way. So notice the difference. It's just the value that you have. How do you use the value you have in relation to the numbers you're given to get it? It might be multiplying values, it might be dividing. So if it's basically division, then this is what will happen. The next one, next example. I can't use so many examples, but I hope the few examples I'm using should actually help. I'm trying very much to make sure that I use different sort of examples to give different ideas. So the second one, B, example, same question. Given that log 2 equals this, log 3 equals this. Find the value of log 4.5. Think about 4.5. 4.5, you see, if there is a 0.5, then it means maybe there is dividing something by 2. And if I divide something by 2, the original number should be this number multiplied by 2. 4.5 multiplied by 2 is actually 9. So if I have a 9 divided by 2, I get 4.5. 9 and the values I have here. Then that simply means this statement is the same as log 9 over 2. But 9 is the same as 3 times 3, then divide by 2. That way. So this now will bring in almost both the two laws that you have learned, because I can see some multiplication and division. So the two laws are supposed to be used in this question. So this leads to log 3 plus log 3 minus log 2. Log 3 plus log 3 minus log 2. Okay, this it. Replace the values. Log 3 is the same as 0.4771 plus 0.4771, then minus 0.3010, which is equals to, I think you can work out this to get the final answer in that case. So looking at this question here, I've actually incorporated the two laws, the first law, and that's why you need to know these laws. I said that for most of the questions that are asked, it may be a question that just involves all these laws, some of these laws, or one of them, or what. So you should just be familiar with all the laws, so that use what is necessary anyway. So now, this is my second example. The third example, which I want you to be very keen, as I explained, still using the same values. If the question was given that log 2 equals this, log 3 equals this, without using tables or a calculator, find the value of log 0.2. First of all, I'm explaining a question that I'm just using one of them. Then we'll use two of them later on. So 0.2, remember there's something I already explained. I explained something to do with 10, which is a common log. So anytime you have logs and you have a number, you don't see the direct way you can use these numbers to get that value, then think of those common logs. So 0.2 is the same as 2 over 10. That's where I start. This is 0.2. But then this is the same as log 2 minus log 10. 10 is a common log. We should not have a problem with that. I've already explained. Then this replace the values. Log 2 is the same as 0.3010. Log 10 is the same as 1. So the next thing you'll do is now you subtract these values. 0.3010 minus 1. And actually if you subtract these values, you'll get negative 0.6990. That. Now this way I want to explain, and this way I want you to listen well. If you're going to do this question, then give this as your answer. You're definitely wrong. So you'll rather listen to this part carefully, very carefully, so that you don't make that mistake in an exam. Based on what I had explained before, maybe some people would think doing this then getting this is correct, but it's wrong. Let me take you back to something you did in Form 2. Think about Form 2. If someone asks you, find the value of log 0.0641. How do you do this? First of all, you write this number in standard form, which would be 6.41 times 10, then raised to, you move two decimals to the right, then it's negative 2. Then the answer would be bar 2 point. Some values here for the characteristic. This value you check from the log table, then this one is this value. The 10 raised to is what comes here, then this. Then you were told something to do with this value here in Form 2. I think they explained to you that this number here is referred to as a characteristic. And the number after the decimal is a mantissa. So there was this rule. The rule was the mantissa can never be negative, but the characteristic can either be negative or positive. Looking at the way I've written this answer here, you know it was logs, then it's minus, then a value that way. So it means that according to my answer, their characteristic is negative and the mantissa is also negative. So it means this statement is wrong, because according to logs, only characteristic can either be both positive or negative, but mantissa can never be. So in such a case, what are you supposed to do? Because without even maybe doing this question, if I asked you that question, forget about what we are doing here right now. We want to get the exact value of that. Then I'll go for the standard form of that, which is 2.0 times 10 raised to negative 1. Then I expect my final answer to be by 1 point something. So now, how do you change this value so that it is in the correct form? Now, there are two numbers here, and I said you have to listen very carefully. I'm only using this one example to explain that. Then, maybe I'll leave you with a question to try later on. There are two numbers here, clearly. There is the characteristic, which happens to be 0. And there is a mantissa, which is a negative 0.6990. This number here can never be negative. That's what I've said. So how do you make this number positive? You borrow 1 from the characteristic. And by the way, anytime you borrow from a number, you get the previous. If you borrow 1, you get the previous 1 digit. For example, if I borrow 1 from 3, I'll remain with 2. If I borrow from 0, there is a number before 0, which is negative 1. So if I borrow 1 from 0, I get negative 1. Of which, now, my new characteristic, because it has to remain positive, it has to remain with the value. If it's either negative or positive, it's valid for the characteristic alone. So if I borrow 1 here, I remain with negative 1. So I'll write that as by 1, meaning that the answer I'm getting is only for the characteristic. Then the 1 I borrowed, I'll add to this value. So it's 1. You say adding, it's like plus minus 0.6990, which is actually the same as minus. So then, if you solve this out, you will end up getting by 1.3010. This is the correct answer. So the correct value of this is actually given by that. I hope the explanation is clear. Once you leave your answer in this form, it means you're wrong, because you're implying that the characteristic is negative and the mantissa is also negative. So that's not the correct way to give the answer. The final answer is this. So there is a trick in that. You should look at that and know how to deal with it. Okay, next one. Next, I'll show one more example, then move on to the next thing. The one that involves the process I just explained here. So look at this question. My next question is, we are supposed to find the value of, now I want to use all the two values, log 0.6. Then 0.6 clearly should be log into brackets 2 times 3, then divide by 10. This gives you 0.6. So according to the explanation, this is the same as log 2 plus log 3, then minus log 10, which is equals to 0.3010, 0.4771 minus 1. And if you work out this value, it should give you negative 0.2219. Again, the same problem. There is a negative here, meaning there is a characteristic which is negative, a mantissa which is negative. Remember, mantissa can never be negative. So the same process, let me take you through the illustration again. My characteristic is 0. My mantissa is negative 0.2219. So since this is negative, I have to make it positive by borrowing something that makes it positive here, which is 1. So if I borrow 1 from this, I remain with 1. The 1 I have borrowed, I add to this value. So it's like 1 plus minus 0.2219, which is the same as 1 minus 0.2219. And the final answer should be by 1.7781. That's after adding the number you borrowed to this. Okay, in this case, I'll have to give you one question, which you'll try on at your own time, maybe. And it is, I want you to try and find the value of log 0.7 to 4 at your own free time. That is it. Okay, now, the next law, which is the third law. We have already covered a little bit of applications as far as expressions are concerned. For the first two laws, the law of addition, law of subtraction. I hope you take that seriously. Okay, next is the law, number 3 law. I promise that we'll do at least 3 laws. Okay, log A base x equals to b. Log A, oh, not equals to, let's say equals to, log A raised to b base x. Log A raised to b base x. So this is the same as, when you see such a statement in logs, it means take the power to be the coefficient of the log. So the statement will read b log A then base x. This is as simple as that. Okay, on paper it looks a very simple thing, but I can assure you that this is a very important law. In fact, maybe for most of the questions that require this topic, this law is the most important. It has several ways that questions need to be applied using it, but in both expressions and equation. And if you're not very keen on it, there are so many questions that you might not actually solve. So like I said, it requires so much. Maybe today I'll only explain some small part of this law, then the next lesson I'll proceed with the law, explaining some more things that are needed to do with it. So first of all, why do you need to know this? It is very important in simplifications, especially in expressions. And the questions, you know, in expressions you're supposed to simplify. When you're simplifying values, you're supposed to write them in the simplest form possible. Consider a number like maybe log 8. Maybe this log 8, written in this form, can be used to solve some other things later on. So log 8 can be written in terms of 2 raised to 3. This is the same as log 2 raised to 3, which is the same as coefficient 3 log 2. The very first importance of knowing this is in questions to do with expressions. I will be fast, so try and understand what and actually explain. Using a very basic example, using this law, I have a question like simplify log 8 over log 2. I'm using 8 because I just explained it some few minutes ago. Okay, in logs, anytime you have over, that is numerator and the denominator, and you're supposed to simplify. Then this question is set in such a way that either the numerator can be written in terms of the denominator in one way or another. So you think of, so with this simple example that I'll use first, anytime you have a log over another log, numerator, denominator, then in between a divide sign, then this means that there is a way in which this numerator or the denominator, either of them, can be written in terms of the other. So looking at this and this law, I can write 8 in terms of 2 raised to. Then this becomes log 2 raised to 3 over log 2. But then, according to the law, the power becomes the coefficient, which will be 3 log 2, then over log 2. Now we all know that when you're dividing same values, the answer becomes 1. So when you divide log 2 and log 2, it's 1. The overall final answer will be 3. So just a simple expression where I'm using this law to try simplify these values, making one number fit the other. Then in that case, you can actually simplify, cancel values, which actually cancel out to get the final answer. So this was some simple basic example. Now a little bit, I'll change. Use something that is a bit harder, but not hard. Say log 12 minus log 3 over log 2. Again, notice the second law of logs. Then there's this over and all that. So if I'm solving this, first of all, I put in mind the second law, which says when you're minusing, divide the values. Then see what I find. And remember what I said, anytime there is an over, a numerator, denominator, there should be, eventually, there should be a way in which the numerator and denominator have something in common. So this said, log 12 minus log 3 is the same as log 12 divided by 3, which is the same as log 4. Then the numerator is log 2. Again, if you got the first example, I don't really need to explain this much. This is just the same as log 2 raised to 2 over log 2, which is the same as 2 log 2, then over log 2. Same, so the final answer would be 2. Another example, a bit maybe slightly harder than this. Okay, the third example I'll show you is log 343 minus log 125 over log 7 over 5. So always notice the slight difference in the kind of questions that I'm using. Now in this question, it's not much different from the others that I've explained already. Just know that anytime there is over, there is a way in which this number must be written in terms of this, in one way or another. So now, this is 7 over 5. How can this be written in terms of 7 over 5? The second law, when you see minus, minus means 343 over 125. Then over log 7 over 5. So, this equation has to be solved because there is a must. There should be a way in which this should be written in terms of this, or whichever. So 343 over 125 can be written in terms of 7 over 5, which should be 7 raised to 3 is 345, 5 raised to 3 is 125. Then this statement here should be the same as log 7 over 5 raised to 3 over log 7 over 5, which is the same as, using our law, has to be 3 log 7 over 5 over log 7 over 5. Then of course, those two will cancel. Our final answer will be 3. Okay, one more example. I could have shown several examples, but now, because of time, I'll just maybe show one more example, then we proceed next time. So one more example I'll show you is log 64 plus log 16 minus log 243 over log 4 minus log 3. Same thing. So to work out this question, you can see in the numerator, there is a combination of both the first law and the second law. So work out this part using that law. In the denominator, there is the second law. So if I simplify this first part here, and in that case, if you can't multiply this often, you can even use a calculator. But make sure that whichever answer you get, leave it in a fraction form. So you'll say, what's 64 times 16 divided by 243? And actually, the answer should be 1024 over 243 over log 4 minus log 3 is the same as log 4 over 3. Just from this statement, I have a number over. And according to how the questions are set and how I explain, there should be a way in which this number can be written in terms of 4 over 3. So that numerator here, if I said 4 raised to 5, I'll get 1024. And if I said 3 raised to 5, I get 243. Then simplifying this would be log 4 over 5 raised to 5 over log 4 over 5, which is the same as 5 log 4 over 5 divided by log 4 over 5. Then eventually the final answer will be 5. So that will be enough for our today's topic. And in part 2, we'll still talk about some few concepts to do with the third law, then move to equations. Thanks for listening. Meet you next time.